Project Retrospective by Grant Tannard. Knowledge graph modeling. For the node, it is any form of entity that contains data or information. In a physical sense, it's the Wikipedia page. For example, it could be a concept like Dijkstra's algorithm, or an acronym like UW, redirects or nicknames like UW, locations like Jakarta, or people like Barack Obama. For the edges, they are relationships between entities or nodes. They contain qualitative descriptions instead of quantitative. In a physical sense, they are edges. The edges are links to other Wikipedia pages. Also means that it's directed as pages points to other pages. For example, here, Simu Liu points to University of Western Ontario, and the relationship is that it is his education. And his birth location is Harbin. Inside the Wikipedia page, as you can see, his education is University of Western Ontario, and his birth location is Harbin. For data structures, one way to implement this knowledge graph model is through a double map data structure. I can store the nodes / entities in a hash map as the keys, and their value pair would be a hash map of neighbors. For the hash map of neighbors, the key is the qualitative description of the edge / relationship, and the value pair is the node / entity it has a relationship to. For the previous example of Simu Liu, here's the key. So Simu Liu is the key, it's a node. And then we perform some hashing and get the value pair, which is the hash map of his neighbors. And some keys are the qualitative descriptions, as I previously mentioned, like the education or his birth location, which each will map to a different new node. So for education, it maps to University of Western Ontario, and for birth location, it maps to Harbin. Next, for modeling the certain Wikipedia pages, like University of Washington. This is a rough diagram, so it doesn't include all the edges, but here we can see that the node is University of Washington, and here are the links to other pages, and there is relationship to them. So for example, for Anna Mary Kaus, this Wikipedia page, University of Washington has a relationship because she's the president of the University of Washington. And here, the state of University of Washington is in Washington, and its city is Seattle, and the type of institution. For the next example, for UW, this is also a rough diagram, so it doesn't include all the edges. As you can see here, it has an edge to University of Washington, and the relationship is it's in the United States, Washington, Seattle. This is also an acronym for University of Waterloo, and the description is Canada, Ontario, Waterloo. And here it can also be like for words, which is unconventional warfare. It's an acronym for unconventional warfare. And then next, for redirect links like UW, it's only one edge, which is just representing a redirect link. So if you say UW, it will immediately redirect to University of Washington's page. For people like Anna Mary Kaus, the same thing applies where this is a link. The edges still are links to other pages. And here you can see that Seattle is another node, and its relationship is the city residents. And here you can see as a relationship to University of Washington, which is she's the president of University of Washington, or the birth city is Havana, and this person's state residence is Washington. Same thing applies for locations. This is Seattle as a node, and you can see the state is in Washington, the county is King County, and the mayor of Seattle is Jenny Durkin. Now for the knowledge graph algorithm. Say we are given a search query UW, a location Seattle, Washington, US, and a result that we want is University of Washington. Based on our knowledge graph, we can find the keywords that represent the nodes. In this case, the UW. UW is a node, that's why it's a keyword. Then similar to a BFS approach, we are going to explore its neighbors with a layer by layer approach until we find the most relevant, which is the popular plus recent / current search UW that is located in Seattle, Washington, US. So here I have the knowledge graph. This is a rough diagram again. You explore all its neighbors and you find the most relevant one. As you can see, this is the most relevant one because it's in the United States, Washington, and Seattle. So this is what we're looking for, and we would return the node University of Washington. For President UW, the search query is President UW, location is Seattle, Washington, US, and the result we want is Anna Mary Kaus. The keyword from President UW is UW. So our goal is to find the president of UW that is in Seattle, Washington, US. As you can see, the term in green here is in our previous example. Therefore, we're able to find a node University of Washington, right? So from the node University of Washington, we can explore its neighbors and find who is the most relevant president. And then we can return the node Anna Merrick House. As you can see here in the diagram, we explore the neighbors. We find that the most relevant one is the current one, which is the Anna Merrick House, which is the 33rd president as well. And then we'll return the node Anna Merrick House. For President Washington, the search query is President Washington, location is Seattle, Washington, US, and the result we want is George Washington. The keyword from President Washington is Washington, but we don't have a node Washington, and the closest thing to it is the University of Washington. However, this will result in our previous one, which is Anna Merrick House, and we want George Washington. So let's add the node Washington instead, which is connected from the node University of Washington. We can add nodes as long as one of the nodes point to it. Now, under the node Washington, we can find the most relevant President Washington, which is the president named Washington, thus adding the node George Washington to our knowledge graph and returning it. As you can see here, I have a diagram. We first add this node Washington because we want this information now. And from the node Washington, we look at all its neighbors and we find that the most relevant one is here, the name of President George Washington. And we add this node and we return it. For president, search query is president, location is Seattle, Washington, US, and result is Joe Biden. Since our location is in the US, the goal is the president of the United States. Based on our previous query, we added Washington and George Washington. Starting from Washington, doing a BFS search, we can eventually check one of George Washington's edges, which is the president of the United States. Then we add the node president of the United States and find the most relevant president. We add the node Joe Biden and return Joe Biden. So from here, we check all of its neighbors, and then eventually we're gonna check all of George Washington's neighbors, and we can see it's the famous for being for president of the United States. So we want to add this node to our knowledge graph. And then once we add that node to the knowledge graph, we can explore that node and find that the current president, Joe Biden, is the most relevant one. And we add this one, and we add this node to our knowledge graph and return Joe Biden, the node Joe Biden. Affordance analysis. Selecting the most popular / relevant ideas from multiple sources is a great way to gather information about current events. However, this includes social risks that may cause ignoring minority views or opinions. Since there may be unpopular ideas that only apply to a small group of people, it may not be considered relevant as many sources don't cover it, therefore being disregarded. For example, a popular idea on the internet may be having classrooms completely shift to online learning, as it makes it easier for students to manage their time since they can do it anywhere as long as they have internet access and a laptop. However, this doesn't consider students who don't have internet access, students who don't have laptops or computers, and also students with disabilities that struggle learning in online classes. So this group of people is being ignored because they are in the minority. My proposal for the next step to improve this issue is by including human reviewers into content moderation. This will allow people to double check on the content that the algorithm outputs and add any ideas that may have been excluded. The New York Times Magazine has a similar approach to this for comment moderation. They have built machine learning technology that has helped them discover which comment seems toxic. However, it is not perfect and they have human reviewers to help review the machine's result. In addition, I believe that it's important to continue improving the algorithm design, such as what is considered relevant or not. Is it because multiple sources have it, or is it because it's from a trusted source? If so, what is considered trusted or not? However, adding in human opinion doesn't fix everything as people aren't perfect, but it's a good first step as we continue to improve this issue. I believe that this applies further beyond this topic. Technology continues to grow rapidly, and with that comes more risk and exclusions. I hope that as it grows, people will continue to monitor it and guide it so that it could be used to benefit society. Thank you so much.